let's talk about how we can actually find the value of R given a set of bivariate data. So in practice, linear correlation coefficients, of course, are found using technology. There is no reason for us to actually do that arithmetic by hand anymore, since we have computers and calculators and all sorts of good things. So we're going to agree to round correlation coefficients to 3 decimal places, and that's almost always what we use. So how do we find the correlation coefficient in the TI? Here's how it is. We will go through this more in just a minute as we do this problem. So let's just skip down to example 6. We have already used our technology to draw a scatter plot of that data about club head speed and distance. So let's just find the R value here. So if we pull up our calculator, and if you recall, our data is already in our list 1 and our list 2, hopefully. If not, go back to the table and put this data back in. After you've done that, second mode to get out of it. What we want to do is go to Stat, Tests, and we're going to go to F, which is Lin Reg T Test. So pick that one and hit enter. XList is our list with our explanatory variable data in it. YList is L2, which is where we put our response variable data. Frequency is always 1 for us. And we also have this funny looking B, which is a Greek beta, and this funny looking P, which is, remember, is a rho. And we want to pick not equal. So we will scroll down to there and hit enter on the not equal 0. And then we'll just go down to calculate and hit enter. So what we want out of this is our R value. We don't have an R value on what we see, but if you look at this little arrow here on the left by the A, that says scroll down. So if we keep scrolling down all the way to the bottom, we get our R value. We do not want the R squared, just the R. So 0.939 when we round to 3 decimal places. So R is 0.939. What does that indicate? It's fairly close to 1. So it indicates that we have positive association. And let's see. If R is positive, it's positive association, and if R is negative, it's negative association. So since it's close to 1, there is strong positive association and evidence of linear correlation. So let's talk about with how we determine whether a linear relation exists between 2 variables. So you might be asking, how do we know whether it's strong enough to conclude that a linear relation actually exists? So we're going to use this, by the hypothesis testing method. which is also called the p-value method. So to do the hypothesis testing method, we are going to use ln reg t test, which is what we just used above to get the R value. And we can get the p-value from the calculator. The calculator calls it p, just like in regular hypothesis testing. And we compare it to the significance level alpha. When we're doing linear regression testing, hypothesis testing, we're always testing the hypothesis that rho, that funny p, equals 0. Which means we assume there is no linear association. If, just like in normal hypothesis testing, if the p-value is less than the significance level alpha, then we reject the null hypothesis, which means that there is evidence to support a linear relation. If the p-value is greater than or equal to alpha, then we do not reject the null hypothesis, which means there is not evidence to support a linear relation between the two variables. So using the data from table 1, which we keep using, we're going to determine if there's a linear relation between club head speed and distance at the 0.05 level of significance. So we want to do stat tests, remember, and then we want F, which is ln reg t test, and our X list is L1, our Y list is L2, frequency is always 1, and the beta and rho, don't worry about what beta is. Anyway, beta and rho, we always pick not equal 0. So let's go back to our calculator and do this. So remember, we go to stat, tests, and then we want option F. List 1, list 2, frequency is 1. Our alternative hypothesis is not equal. And then we're just going to say calculate. So we had to scroll all the way to the bottom to get our R value. Our P value is right here where it says P equals 5.498. Remember, a p-value is a probability, so it cannot be bigger than 1. And so we have to look out for this e to the -4 over here to the right, which is scientific notation. So we have that our p-value is 5.498 times 10 to the -4, or 0.0005. If we compare that to alpha, which is 0.05, we have that the p-value is less than alpha, which means we reject the null hypothesis, which means that evidence suggests there is linear correlation between club head speed and distance. Now, the p-value does not tell us whether we have positive association or negative association. We need the R value for that. It only tells us whether or not we have linear correlation. And the last thing we need to do is talk about the difference between correlation and causation. We saw in chapter 1 that observational studies do not allow a researcher to claim causation, only correlation. Sorry, only association. However, designed experiments control certain variables, which allows for a researcher to identify cause and effect. And since we can identify the cause and effect relationships among variables in the study, if the data used are observational, we cannot conclude that two correlated variables have a causal relationship. That is, that one causes the other. For example, a strong positive correlation between ice cream sales and shark attacks cannot conclude that eating more ice cream causes more shark attacks. And that's because the data are observational. There's clearly a lurking variable related to both the explanatory and the response variable, and that is the weather. Obviously, as the temperature rises, both ice cream sales and the number of shark attacks increased. So be careful, just because there is correlation does not ever mean there is causation unless it was from a controlled, designed experiment. If it's just observational data, then there is no way we can say that one thing causes another. So, correlation does not imply causation.